Now, as I said, we can compute square root of n using addition, multiplication, division, and subtraction. Now, the way we can do that is by using this observation. So you are given an input number n that is greater than 0, and we want to know how close I need to get to the number that I want with a precision p, because square root of n may be not an integer, in which case identifying it precisely is impossible. So we want to say that I want square root of n with certain precision. Then this amounts to finding a number a such that a times n divided by a is equal to n. And we want a and n divided by a to be close enough. So essentially this means that we have found two numbers that multiply to n, and those two numbers are really close to each other. That means each one is actually almost equal to square root of n. So we can do it as follows. We can have a guess for a, and once we have a guess for a, we can compute the next guess by the following algorithm, which is you take half of the old guess plus n divided by old guess, and that will be your new guess, and you keep repeating this until you get close enough to. The procedure to compute square root of n, we could think of it as like this. First you assign a to some value, in this case just 1. You set b is equal to n divided by a, and while a is not equal to b, and this is where that precision that we want is going to play a role, and we will see how that comes in with the Python code in the next slide. We are going to compute a to be the average of a and b to be n divided by a, and we keep repeating until we get to a point where we find the answer that we want. So in this example, I would have a is 1, b is 3. So in the first iteration, a will become 2, b will become 1.5, and we'll keep repeating this until after 3 iterations, because our precision is just 2-digit long, we will eventually terminate at a is equal to 1.73. Now, since representation of real numbers will go on forever, what we want is we want to use the precision to know whether we have gotten an answer that is close enough. And here what we have done is, instead of saying a is equal to b, we are saying that the difference between a and b is small enough. So if the difference is more than the precision, you keep repeating. If the difference is less than the precision, you stop. The next algorithm I want to talk about is for GCD, greatest common divisor. You have learned what GCD is. You probably have also studied methods to compute it. The method that we are going to study is one by Euclid. The reason we are going to study this method as opposed to the one you studied in probably middle school, which was to find factors to find GCD, is that finding factors is a hard thing to do, whereas computing GCD is relatively easy thing to do. And Euclid's method allows us to find GCD in a more efficient manner. So what is the GCD? It is the largest positive integer that divides both m and n, which are the given two numbers. So we can ask the question, what is GCD of m comma m? The answer is that it is m. For each of the questions, feel free to pause in case you want time to work on it. What is GCD of m comma 1? Well, the only factor 1 has is 1, so it's going to be 1. What is GCD of m comma 0? Now this is a somewhat tricky question. The answer is m. The way to think about this is, if I take any number, then it divides 0 evenly. If I take any number other than 0, it divides 0 evenly. In other words, 5 is a factor of 0, 6 is a factor of 0, 1 million is a factor of 0. All positive integers are factors of 0. In terms of m, the largest factor it is going to have is m itself. If m is evenly divisible by n, then what is GCD of mn? And the answer is that it is n. So let's look at this question of what is GCD of 115 and 544. Euclid's algorithm for computing GCD is as follows. This is one algorithm I want you to study carefully because it is something that we would be using in other parts in our course. So here we have two positive integers m and n. We start by dividing m by n and computing the remainder r. If r is 0, that means n is a factor of m, in which case the GCD is n and we terminate. Otherwise, we set m is equal to n is equal to r, and repeat. So, first of all, we want to make sure that it is an algorithm. To do that, we can see that each step is definite. The only thing that is challenging is whether this is going to terminate, and if we do some analysis, we will see that it will eventually terminate, because if I look at this, r is going to be less than n. So if I just focus on the parameter n, the first time I'm calling it with parameter n, next time I'm calling it with r, and r is definitely smaller. So that means the second parameter keeps getting smaller every time, and that means eventually it will get to 0, and when it gets to 0, the algorithm will terminate. So let's try with this example 119 and 544. So let's in the first iteration, m would be 119, n would be 544. When I divide, the remainder would be 119. So we go to the next step. Now, in the next step, what we are going to do is we are going to set m is equal to n is equal to r. So that means m will become 544, n will become 119. So now in the next iteration, the remainder would be 68. This will require a little bit of math, but I can ask you to check that. Again, we continue. Now we will start with the numbers 119 and 68. That will give us the remainder to be 51. Keep going, and eventually we'll get to the remainder is equal to 0. At this point, we will get n is equal to 17. That means the GCD is 17. Note that 17 can be expressed as a linear combination of 119 and 544. So in this case, 17 I can write as 2 times 544 minus 9 times 119. Two numbers are said to be relatively prime if their GCD is 1. In other words, if they have no common factors, then we say that those two numbers are relatively prime. So for example, 10 and 21 are relatively prime. Even though 10 is not a prime, 21 is not a prime, 10 and 21 do not have any common factors, and that means that they are relatively prime to each other. Another thing I want to mention here is this observation that we made over here, which is that the GCD can be expressed as a linear combination of the two numbers that we began with. This is true for all numbers, and this is something that we would use subsequently. One of the things I'm going to ask you to think about is how do you find these numbers in a systematic fashion? Now, I don't want you to find these numbers by trial and error. I want you to adapt this algorithm to figure out uh, how to compute these numbers over here. While I will talk about how to compute these numbers subsequently, I want you to think about this because this will help you understand this algorithm better, and it will also help you understand some of the cryptography applications that we're going to do later. So why does this algorithm work? The way it works is something like this. So let's say I can write m as some number d times n plus r. For sake of discussion, let's say the GCD of m and n be the number g. So what does this mean? This means m is a multiple of g, n is a multiple of g. So if I write this in terms of m as a times g, n as b times g, then I will get this equation that says a times g is equal to d times b times g plus r. Note that what you have is I can write this expression now r in terms of these other two terms, and both of these terms have a factor g in them, so I can take it common, and that means I will get it something like this: r is equal to g times a minus d times b. This means that g is also a factor of r. So what we did, if you recall, was we basically replaced GCD of mn. We said this was going to be computed as GCD of n comma r, and in this case exactly this is what we are going to get, because g is also going to be a factor of r. There is another thing that we want to define in the context of GCD, which is the phi function. Let phi n denote the number of positive integers not exceeding n that are relatively prime to n, where we are going to count 1 is relatively prime to all integers. So let's look at an example. By the way, before I get to example, phi n is known as the totient or the indicator function. This is the total number of numbers that are relatively prime to the given number. So let's look at an example, phi of 24. So these are numbers that are relatively prime to 24. So in this case, I will have 1. 1 is always included. I will not have 2, even though 2 is a prime number. It is not relatively prime to 24 because GCD of 2 and 24 is 2. Then I do not have 3, I do not have 4, I have 5, then I have 7, 11, 13, 17, 19 and 23. Let's look at this question. I have some code. I would like to know if this is an algorithm. I'm given an input integer x which is greater than 1. The algorithm says if x is 1, stop. If x is even, then make it smaller by dividing it by 2. If x is odd, make it bigger by multiplying 3 times x plus 1. And in both steps 3 and 4, afterwards go back to step 1. Go back to step 2. So let's look at an example. If I have input x is equal to 7, that's odd. So multiply by 3. add 1, that will give me 22. Then this will give me 11. 11 is odd, so multiply by 3 uh, and add 1, so that's going to give me 34. And if we keep going, eventually we come to 1, at which point we stop. Now the question is this something that will happen all the time, or for certain inputs this will not happen? So what I'm going to ask you to do is try this for different values of x and see what your observation is. If you have some thoughts on whether this will always terminate, this may not always terminate, you can let me know and we can discuss this in class. Once again, we have reached the check before you go ahead slide. I want to make sure you have understood how Euclid's algorithm for finding GCD works. Note that the algorithm you learned in middle school, where you find factors and choose a common factors, that algorithm is useless in practice, especially when the numbers are large, because factoring a number is a difficult thing to do. Sorting algorithms are not very important as far as this class is concerned. Just a basic idea of what sorting looks like is important. The details of the algorithm are stuff that you will cover in 331. I want you to review the torsion function that we described. It will be useful in the next few modules. And once again, it is the number of numbers that are relatively prime to a given number n. So if I start with n equal to 15, all numbers that are relatively prime to 15 would be the torsion function for 15. We have reached the end of the module, so I want you to go ahead and do the review quiz for this module.